Hi everybody, welcome back to my channel on Feynman integration. We're going to be doing something that I don't normally do in this video today, which is actually, I'm going to start with a blank whiteboard and we're just going to do it step by step, and I'm going to be writing it out. And I encourage you to pause the video, in between steps and see if you can take it all the way to the end. But anyway, the integral we'll be evaluating is the integral from 0 to infinity of the natural log of x squared plus 1 over x squared plus 1 dx. And looking at that, I haven't verified this, I haven't tried it this way yet, but it looks like you might be able to use King's property on that. Because when you see x squared plus 1s, that screams for the substitution that x is equal to the tangent of u. And I might try doing that in the next video if it turns out that way works. But in this video, we're going to be using Feynman integration using the Leibniz rule for differentiation under the integral sign, which, if you've watched my videos, you should all be very familiar with by now. Okay, so, well, let's see. First thing we do, like always, is we create a new function. We insert a new variable to create a new function. In this case, the function we'll be creating is this. I'm going to say that f of t is equal to the integral from 0 to infinity of the natural log of t x squared plus 1. And this is kind of a preference. I like just putting t there. You could put t squared and work it out also. x squared plus 1 dx. So that's our function of t. Next step, like always, is we are going to use the Leibniz rule for differentiation under the integral sign to take a derivative of this function of t by taking a partial with respect to t of the integrated. So what we do if we get that is that our function f prime of t is equal to the integral from 0 to infinity of, okay, well, let's do this out. We're going to have the same denominator because with respect to t, those x's are constants, and of course we will have a dx. All right, well, when you take the derivative with respect to the partial with respect to t of the natural log of tx squared plus 1, you will get back an x squared, canceling out this x squared. And then you will have 1 over this part inside the natural log. So let's see if I can squeeze that in there. Tx squared plus 1. So that's it. That's our f prime of t. That's a nasty integral, but you can do it using partial fraction decomposition and then just some pretty standard integration techniques. I'm gonna walk through some of it. I'm not gonna be performing the partial fraction decomposition on the board because that's a long, involved process. You all know how it goes. Basically, we would set that partial fraction decomposition up this way. We want 1 over tx squared plus 1 x squared plus 1 to be equal to some constant a x plus b over tx squared plus 1 plus cx plus d over x squared plus 1. And from there, we would create a common denominator. We would multiply this part by this and this part by this. That way we would have all the same denominator. Therefore, we could ignore the denominators. And essentially what we would have is that this times this plus this times this must equal this. And then it's a lot of, and then that's a lot of algebra, but you can solve for A, B, C, and D that way. I'm sure you all knew how partial fraction decomposition worked, but for those of you who didn't, there you go, that's what you do. And that's how you break that up into two separate integrals that you can evaluate. But let's see, what you do if you perform that partial fraction decomposition, and I have to cheat right now, I have to use my notes, is you will get that, I'm going to have to write small, f prime of t is equal to, let's see, you get t over t minus 1 times the integral from 0 to infinity of 1 over tx squared plus 1 dx minus 1 over t minus 1 integral 0 to infinity of 1 over x squared plus 1 dx. Right. So if you perform that partial fraction decomposition and do some rearranging and factoring out and all that stuff, you can arrive here. Let me double check to make sure that that's right, and I have not written that down incorrectly on the board. I'm not good enough to check all this stuff in my head. I have to do it out in advance. Okay, no, that looks correct. So these are pretty simple. Well, I won't call them simple, but those are standard integrals, and I'm sure all of you can evaluate those pretty easily. You know, it's about they're each about 5-minute integrals. So go ahead and do that if you want. But if you do that, if you work that out, you will get something like this. You'll get f prime of t being equal to pi over 2 times the square root of t minus 1 over t minus 1. So now we have f prime of t, and as you all know, we don't want f prime of t, we want f of t. So we go like this, dt, and like this, dt. I apologize for my sloppy integral signs. I'm not very practiced at writing on whiteboards on the fly, but actually, you know what? I'm going to fix that. That is disgusting. Okay. That's kind of a tricky integral right there. You know, that would probably be like a challenge problem on a Calc 2 test. It's not super obvious what, well, it is. I think most people would recognize that that square root is kind of annoying. So most people would pick this substitution, and it turns out that it's the correct substitution to make. Excuse me. That substitution is that t is equal to u squared. Because that way we can get rid of that square root of t and it would just become a u, and it'll be a lot nicer. So that gives us that dt is equal to 2u du. Okay. So let's go ahead with that. Let's make that substitution. Oh, and this, of course, will be equal to f of t, and then you'll get a plus c. Let's see. F of t is now equal to pi over 2. Now we're going to insert our substitution. Times the indefinite integral of the square root of u squared, which is just u, minus 1 over t, which is u squared, minus 1 dt, which is 2u du. We'll use that 2 to cancel this and make it a pi. So we've used the 2, and now all we have to do is distribute the u, which will give us a u squared minus u du. There we go. A couple different ways you could proceed here. Well, first of all, what I could have done originally is not distributed that u. I could have kept this as u minus 1 instead of distributing that u in there to get u squared minus u. Let me make sure I've still got this correct in my notes. Yeah, that's right. And then from here, we can rewrite u squared minus 1 as the difference of squares, or we recognize that it's the difference of squares. And then you get u plus 1 times u minus 1. And of course that and that will cancel, leaving us nothing but pi times the indefinite integral of u over u plus 1 du. Usually when I see things like this, I approach these integrals like this. I hope you all agree that I can just add 1 and then subtract 1 like that. So then this becomes f of t being equal to pi, and we'll now use the linearity of integrals to split this up into u plus 1 over u plus 1 minus 1 over u plus 1. So this just becomes f of t equals the indefinite integral of du minus pi times the indefinite integral of 1 over u plus 1 du. So f of t is now equal to pi times u minus pi times the natural log of u plus 1 plus c. That means f of t is equal to pi, well, u is the square root of t. So that's pi square root of t minus pi natural log square root of t plus 1 plus c. Okay, we need to get rid of that plus c now. How do we do that? Well, we got to find a value for it at a point. Luckily, that's easy to find. If you plug in f of 0, we get that f of 0 is equal to the natural log of 0 plus 1 over something. In other words, it's 0. We know that f of 0 is equal to 0. So, plugging that in, we get that, well, I'm not going to write this part out. We get that 0 is equal to pi times 0. So this part cancels out. Minus pi times the natural log of 0 plus 1, natural log 1, 0. You get that 0 is equal to c. So we can just go ahead and calm down, guys. That's it. That's our final expression for f of t. Well, now how do we find I? Obviously, all we do is we plug in 1 for t. And plugging in 1 for t here is exactly the same as plugging in 1 for t here because they're equivalent. We just showed that. So, f of 1 is equal to I. Okay, so we plug in f of 1 and we get I. And that's equal to, let's see, pi times 1, which is just pi, minus pi times the natural log of, let's see, square root of 1 is 1, 1 plus 1 is 2. That would be the natural log of 2, which is equal to pi times 1 minus the natural log of 2. I want to make sure that's actually the right answer. I'll have to punch it into my calculator here. Pardon me 1 second. I'm pretty sure that is the correct answer. Let's see. Pi 1 minus natural log 2. About 0.964. Yep, that's correct. So, yeah, that's it. Step by step, that's how you get that the integral from 0 to infinity of the natural log of x squared plus 1 over x squared plus 1 dx is equal to pi times quantity 1 minus the natural log of 2. Anyway, I hope you enjoyed that different format. I know this is, I usually have it all written out on the board up front, but I kind of wanted to practice doing it this way, just to get more comfortable with performing steps on the fly on the board, because I'm not very good at that yet. But anyway, thanks for bearing with me, and I hope you enjoyed that.